something that we do here when we have an activity, like a workshop or a school, is to invite one of the lecturers to give a colloquium to our community of students and professors. So it's a pleasure. Maybe you have to.
This
is off.
Yeah.
This is off. So it's a pleasure to have here Professor Pedro Leite Diaz. He has a very large CV, so I just highlight a few things.
White hairs.
And white hair. I'm glad I'm dressed up because he's a very important person. So Professor Pedro, he got his bachelor's in applied mathematics at the Institute of Mathematics and Statistics of USP. And then he did his PhD at the State University of Colorado. And he's now a full professor at the Institute of Astronomy and Astrophysics and Geophysics.
And atmospheric science.
And atmospheric sciences of the University of São Paulo. And currently, he's also the director of this institute. So he's a full member of the Brazilian Academy of Sciences, of the Brazilian Academy of the São Paulo State Academy of Sciences. He received a very important prize, the, I don't know how to say that in English, Ordem do Mérito Científico. And he was also president of the Brazilian Society of Meteorology. The list goes on and on. And has published more than 135 scientific works, has supervised more than 65 students. I will tell you that I don't remember all the names.
Yeah.
And he's an expert in questions of weather variability and weather changes and environmental impact. So it's a great pleasure to have Professor Diaz, who's going to talk about dealing with uncertainties in weather and climate prediction.
Okay. Well, I'll like to start talking a little bit about motivation. Of course, I had several reasons to study this problem since for the last several decades. But about 10 years ago, I came to me the attention to this page. Very interesting discussion on whether meteorology is a science or not. And look at this last sentence. One of the purposes of this science called meteorology is to forecast. And it cannot do it with any degree of accuracy. So is meteorology a science at all? Well, this question actually kind of hurt me, because I've been working in this for so many years. I truly believe that it's a science, and you'll see this kind of comment. So let's try to understand what's going on and why I'm interested in this issue. First of all, we have to remember that the atmosphere is a pretty complex system from the point of view of being a multi-scale and multi-physics problem. So it's a complex problem. So you have tornadoes, that's a few tens of meters to 100 meters or so. You have hurricanes, several hundred kilometers. You have fronts that are several thousand kilometers long. And you have a fluid that is full of different types of instabilities. And from an energetic point of view, you're talking about a system that you have the interaction between the atmosphere, the ocean, the surface. The interaction with vegetation is very important because it connects from a point of view of energy transfer, sensible heat transfer, and latent heat transfer at the surface. You have ice with different very important properties from the point of view of reflection of shortwave radiation. You have the clouds. Clouds are very complex. Actually, it's a discontinuity in the atmosphere, right? You have no cloud, very sharp boundary, very important properties from the point of view of the radiative transfer, from the point of view of heat transport. It's like an engine that transports energy from the surface. The excess energy at the surface goes to higher levels in the atmosphere through clouds. And you have to model this complex process. Basically, it's the momentum conservation, mass conservation, air, water, trace gases, aerosols, because all these things take part in the energy balance. And of course, the energy conservation. As I mentioned before, you have different scales in the atmosphere. You go from a few meters or up to the planetary scale, and the time scale from a second to, years. And these processes are connected. That's something that for many decades, I've been very much interested in understanding the scale interaction in atmospheric motion. But as I mentioned before, it's not just multi-scale, time and space, but also multi-physics. From the point, strictly from the point of view of the atmosphere, you basically have the momentum conservation equations. The colors here refer to typical approximations. For those that are more familiar with these equations in the atmosphere, the red terms are ignored when you have the so-called traditional approximation, which is valid if the height of your model atmosphere is not too high up. And that used to be a good approximation, but now most of the forecasting models go up to 50, 60, 70, up to 100 kilometers. And then most of the more modern models include the red terms. The hydrostatic approximation here, where you have the vertical momentum equation, you have if you ignore the green term and the red term, you have the hydrostatic balance. The pressure, gradient, force, and the gravity are balanced. And the mass conservation, you have a series of these equations for air, for water, water vapor, liquid water, ice. Ice appears in different forms. And you have other gases like CO2, ozone, and so on. So most of the climate models have perhaps 40, 50, 60. Some have more than 100 variables in the mass conservation. And first law of thermodynamics, you have the adiabatic heat sources and sinks that are pretty complex, in general nonlinear dependence, and represent processes like the cloud, the latent heat release in clouds, the radiative processes, and so on. So in a very simplified way, when you talk about modeling climate, for instance, you have an equation for the atmosphere. L represents the linear part, and the nonlinear, F is the forcing term. Another set of equations for the ocean, for hydrology, for ice, and so on. We have merged everything together in this equation. The third one is the soil. The fourth is the vegetation, as I mentioned before. XC is the chemical species. And here you see what these variables represent. XA is the wind, temperature, water in different forms, and so on. Water is the ocean current, temperature, salinity, and so on. Soil temperature, soil wetness, nutrients, and so on. Nutrients actually appear in the vegetation model. The vegetation model contains terms like, for instance, the volatile organic compounds that are emitted by vegetation and condense in the atmosphere, form aerosols. The aerosols interfere with the radiative balance or the cloud microphysics. So these VOCs appear in several places, and they have an important role, for instance, in as a diabatic heating term in the equations, because they interfere with the condensation process. The problem in climate models is the size of this animal. Just the atmospheric model, even for a very, let's say, coarse resolution model, you're talking about 10 to the 9th. So this XA, the dimension is about 10 to the 9th. Weather forecasting usually uses higher resolution models. You're talking nowadays 10 to 11, going to 10 to the 12. And then you have all these other models. So it's from a computational point of view, it's a complex process. And as I mentioned before, the subgrid processes associated to the clouds are very complex, introduce a lot of nonlinearities in the process, and the aerosols, including the gases. Yes?
So you say conservation momentum. Conservation momentum of what? Of the air or all the
Yeah. We usually deal with a mixture of all these parcels. And actually, we have ways to deal with the fact that you have a combination of gases, or if you have the aerosols in general, the mass is very small. So it does not interfere in the momentum conservation. But water is an issue.
So I have a question. So this model is very complex.
Very complex, yeah.
But my question is this: so the model is accepted, or there are different models that are?
There are different models, and that's as I'm going to show later. That's how we deal with part of the uncertainty, using an ensemble of forecasts from different models.
Different model, different parameters?
Different parameters. The processes are pretty much the same. But the way you represent these processes, there is uncertainty in the way you formulate mostly the heat source and the momentum source. And in the IPCC, the International Panel for Climate Change, that's the time evolution of the complexity of the models. Back in the late 80s, mid-80s, the models used to have just the atmosphere, a very simple land model, and a very simple ocean ice model. And they're becoming more and more complex. Actually, for the next IPCC, you also have the human dimension, some interaction with the human dimension is important because of the emissions of greenhouse gases. So economy and climate are related. About 10 years ago, I had a PhD student. He had a very simplified model for the global economy and a very simplified model for the mean global temperature. Very interesting relationship. Actually, he used things related to game theory and multi-agent modeling to model the outcome of the climate convention decisions on the reduction of CO2 emissions. That's very, very tricky. So, and we deal with uncertainty from the point of view, as you saw before, you actually have an initial value problem, and somehow you have to have observations, have to have a combined observation with an initial guess of the state of the system, and in order to produce the best possible initial condition for the model. And as mentioned before, the model is not perfectly known, right? There are variations in how you formulate the physical processes, the spatial resolution, then there are some numerical issues as well, and the discretization, and F is actually a multivariate function. So there's the physical interactions among components, not completely understood in some cases, uncertainties in parameters, so you have to deal with all these things. And okay, so let's go more in detail on the origin of the uncertainties. The nonlinearity is an issue of the prediction problem. Probably most of you have know the work by Lawrence back in the 60s. Actually, his work was predated by Edie in 1949 and Thomson in 1957, who already dealt with some of the problems that he formulated in the 1963 paper. This famous paper by Lawrence back in '83 is the one that studies the, and he points out basically in this paper that the predictability would not go beyond a few days based on a very simplified model of the atmospheric flow. This paper was a landmark in understanding the stability of dynamical systems. He showed, for instance, that small variations in the initial condition produced significant differences in the forecast after a few days. Something that, from the operational point of view, people already had this result. Back in the 50s, for instance, those times computers didn't have much memory, and you had to download the memory in the computer to punch cards. And when you do that, you chop down the digits, you know. And people realized that in some cases, the results were completely different after 24 hours. And that's what motivated Lorentz to study this problem. So let's go back now to a very simple dynamical model, because otherwise it's difficult to study. And this is the simplest set of equations that describe the atmosphere or the ocean. It's called the shallow water equation. So it's model equations that describe an incompressible, homogeneous fluid. In spite of the fact that it's incompressible and homogeneous, it's still quite useful. Right? It describes a series of important aspects of the atmospheric and oceanic circulation. In a compact way, that's the shallow water model. You have a linear operator, a nonlinear, and eventually a forcing term. And if you look at the L operator, it has some very nice properties. First of all, the eigenvalues are all real, and the eigenfunctions form a complete set. That's quite useful. In other words, you can actually expand, and you have the eigenvalues that depend on the zonal wave number, a sort of meridional wave number, and wave types. That's the dispersion relation. So you have a set of eigenvalues that are rather small, in other words, slow frequency, and some waves that are much faster, the inertial gravity waves. But you don't have a full separation of the slow waves and the fast waves. There's this wave here is called the Kelvin wave, propagates to the east, non-dispersive, the linear relation between omega and the wave number. And there's this other wave here called the mixed Rossby gravity wave. So these two waves connect the high frequency with the low frequency. This scale separation is very important, as you'll see later. So if you have this nice property about the eigenfunctions, you can expand the variables in a series of these eigenfunctions. So you have different manifolds associated to the slow motion, to the fast motion. And if you plug this expansion back into the original equation, you end up with this very nice harmonic oscillator, nonlinear harmonic oscillator model. This is the interaction coefficient. That's the nonlinear part. and the forcing part. And depending on the geometry of the problem and so on, you can actually compute these interaction coefficients analytically. So it's very nice for theoretical purposes to work with this kind of model and then explore the role of nonlinearity. Of course, nobody really uses this model for operational purposes. It's very expensive from the computational point of view, but it's very useful from a theoretical point of view to understand what's going on. And you can actually separate the flow into a slow component, a fast component, and back in the late 70s, early 80s, it became quite popular, this idea of, first of all, from observations. Quite often, you see the fast components pretty much in balance in terms of the linear part, the nonlinear, and the forcing. This was called a slow manifold at the time. This was, I think the first ideas came out in the 76, 77, more or less. Actually, my PhD thesis at the time was on the role of the forcing term in establishing the dynamics of the slow manifold, more than 40 years ago. So if you have this kind of balance, the fast component is dependent basically on the structure of the slow component. The evolution of the evolution is given by the slow component. At that time, back in the mid-70s, the concept of slow manifold was basically just the effect of the nonlinear terms. So this set of equations that you actually need is this set. This solves your problem, in principle. And the idea of the slow manifold, that's the classical slow manifold. At that time, it was called the nonlinear norm mode initialization, because that's a very efficient way to define the initial condition in this filtered world and avoid noise produced by the fast component, not imbalance. So people used to believe that the fast component was not really important for the evolution of the synoptic scale, in other words, fronts and so on. But by the end of the 70s, early 80s, it became quite clear that something was missing, and that is the introduction of the of the forcing term. And it ended up by the end of the 80s, early 90s, it was coined the role of the convectively coupled waves. Why convectively coupled wave? Convectively because clouds need divergence, convergence, below divergence aloft. And if you have convergence, that's a characteristic of the fast modes. The slow modes are more rotational, and the fast modes are highly divergent.
You said fast and slow. You mean the frequency is higher for fast than for slow?
Yes, yes, yes.
What is capital F and capital S?
Capital F. Oh, here is a collection of all the fast modes. In other words, you merge all the fast modes in one. And here is just the slow modes, all waves. And so in general, what you have, this is the blue version here, is the complete, what's called the slow manifold nowadays, which is a combination of the nonlinear role and the convective, the clouds and the radiation and so on.
So if I understand correctly, this slow manifold is an approximation.
Is an approximation.
Can you check it numerically?
Yes, you can. Yeah, and it works, and for large-scale features, it's a good approximation. But of course, now, if you're really interested in details, or if you're going to very high-resolution models, that doesn't apply, right? Because in the very high resolution, you have fast waves all the time. And actually, it's important to also to explore the impact of these fast oscillations in the slow. And actually, that's something that I've been working on for the last 20 years or so, and showing the importance of the fast modes in controlling the evolution due to, for instance, nonlinear resonance. Okay. Oh, and these are the trajectories. So when you start with initial conditions from any point, if you have this old version, the atmosphere, starting from any place in this diagram, tends towards the slow manifolds. And there are several interesting papers showing that this is true. In other words, if you start away from the slow manifold, the solution evolves towards something that's called a slow manifold. And if you have forcing, the clouds, for instance, you go to the red one, or in the real world, you go to the blue one. Now, you can explore how the structure of the interaction coefficients. And for weakly nonlinear problems, you can actually find analytical solutions. And you have the nonlinear resonance. And then in that case, if you don't have forcing, you have the linear growth of the energy and so on. So you have different types of instabilities. And if you have the triads, you can explore, for instance, resonance involving rotational mode and gravity modes. And it's curious, the fact that even with the shallow water model, you find a correspondence between some of these resonant triads and things that you observe in nature. Just the atmosphere and a simple triad, and it helps understanding some important features. It's more interesting to explore connections between two triads that share one term. So you have 5 terms. Actually, that's the kind of model that was very much explored by Lorentz, but look at the date. Now, oops, that's kind of difficult. I think it's 87. 87. So years after he wrote the first paper, they put together a very simplified model. And if you look at the structure of this model, it's exactly the previous slide. You have a forcing term, you have dissipation in this case, you have a linear component, and you have the interaction among the coefficients. He was actually studying this, the stability of 2 triads that share one common term.
That's a linear model?
No, it's non-linear. It's non-linear. Yeah. And if you go back to the previous slide, for instance, these are the non-linear terms, right? And that's the forcing in the linear terms. And then back in 1991, this guy, Jacobs, he questioned the existence of the slow manifolds in a model system of equations because of these issues about stability. A very nice work. If anybody's interested, I think it's worth reading this paper in order to understand the hypothesis behind Lorentz's work and why this slow manifold is not stable in some situations. If it's not stable in some situations, it brings this question of predictability, right? And so that's the origin of Jacobs' argument. And then a year later, Lorentz published a paper, The Slow Manifold, What is it? Very nice discussion on the dynamics of the slow manifold. And actually, what makes this argument very interesting is the fact that he introduces the role of the forcing term. And you'll see in a few more slides why this forcing can be interesting. It comes out in the case where you have, for instance, ocean and atmosphere. You may have triads in the atmosphere, triads in the ocean that interact non-linearly, but the ocean has a completely different time scale compared to the atmosphere. So the fact that you have the slow component, the ocean, forcing the atmosphere, increases the predictability. And that's the reason why starting mid-90s, late 90s, climate forecasts obtained from dynamical models got better results than the purely statistical forecast that used to be operationally produced until the mid-90s. That's another, going back to this issue about uncertainties, that's another very important paper by Edward Lawrence, the tractor sets and quasi-geostrophic equilibrium. He basically, in this paper, he puts together lots of things that were in the literature concerning atmospheric balanced flows since the 30s. I find this paper fantastic from this point of view. The puts everything together in a very simple way.
So is it correct to say that the predictability has to do with this attractor behavior of the
yes,
equation?
yeah.
That's why things
Yeah,
are predictable.
exactly. And I got very interested in these issues because we had some observational evidence of interactions between fast time scales like diurnal variation, diurnal variability, 24-hour period, and the intraseasonal time scales in the atmosphere, 20 to 60 days. In the early 2000s, there was a lot of concern, a lot of discussion in the literature trying to understand the reason for the intraseasonal scales. People couldn't find really unstable modes from a linear point of view, or even with a variable basic state, or nothing really explained what we knew at that time about the dynamics of the intraseasonal scale. If you look at the power spectra in the atmosphere, there's a big peak of energy in between 20 and 60 days. And of course, there's a lot of interest in predicting these scales because of the applications. For instance, in the energy sector here in Brazil, that's what they are pretty much concerned. They want to know the precipitation prediction, the time scale of 20, 30, 40 days. Agribusiness as well. And unfortunately, we knew very little at the time. Most of the models were not able to reproduce the power observed in the interseasonal time scale. And actually, this series of paper by Carlos Haupt, Carlos actually worked here, right? Yeah. From the point of view of the interaction, nonlinear interaction between the fast and the slow, in this case, it's called what meteorologists call the synoptic scale, 5 to 7 days. So the interaction between one day and these waves produce resonance in the scale of 20 to 60 days. And we explored the diurnal variation. And then more recently, we explored the interaction with the ocean that I'll talk about in a minute. We realized at that time that just the atmosphere was not enough to fully explore, to fully explain what was going on in the atmosphere at the 20 to 60 day variability. So we found a part of the problem, but not robust explanation. And the idea was, okay, what if, as Lorenz had done before, why don't we introduce the ocean in this process? And again, I'm not a very good swimmer, therefore, shallow water models are safer, right? And we decided to explore the possibility of coupling a shallow water for the atmosphere and a shallow water for the ocean. And the idea was to try to understand the role of the so-called thermohaline circulation that pumps warm water to the north in the Atlantic, cold water south here, and it's connected to the Indian Ocean and to the Pacific Ocean. And the motivation was actually, again, this paper by Lorenz. He connected a fast mode and a slow model, and Chardy and Shukla, back in the early 80s, they were the first to put together this coupled oscillator and explore the possibility of having some predictability in the model, Lorenz model, if you have a forcing term. And a few years ago, one of my students, Enver Ramirez, who's now at CPTech, he published this paper on the multi-scale atmosphere-ocean interaction in the long-frequency variability in the equatorial region. And the idea, as I mentioned before, is to study this coupling of waves in the ocean and the atmosphere, and in order to produce slow variability. So what he did was basically a multi-scale model. So he has a model for the atmosphere, another one for the ocean, and they interact through different processes, including the physics, which is very important in this case. If you turn off the physical process, like precipitation, this mechanism goes away. We also explored the possibility of having interaction, more complex models, and something that I can't resist telling you a story about these equations. Whenever I was working on this model, at some point I told him, okay, let's do it numerically, because I thought it would be very complicated to find analytical solutions. Enver basically refused to proceed with the numerical solution. He said, I can find the, and it took a bit of time, but he ended up producing very nice results with analytical solutions for the interaction coefficient, which I just couldn't believe at the time. And in his paper, he discusses the possibility of having, through this interaction between the atmosphere and the ocean, long-term cycles. For instance, you're talking about periodicities of the decadal time scale, multi-decadal, and they come about, the origin of this is an interaction between the intra-seasonal time scale, interannual time scale, interacting among themselves, and throwing energy into the decadal time scale. This, I think, was great in the sense that we had an internal mechanism in the sense that it has to do with the interaction between the atmosphere and the ocean, connecting variability in a fast time scale. In this case, it's the intra-seasonal, 20 to 60 days, up to decadal. Actually, at the time when we put these things together, it became quite obvious to me that in some cases, when we are always complaining about the fact that the models, those complex models from the beginning, quite often they do not have enough power in the intraseasonal or in the decadal, multi-decadal time scale. And then you scratch your head and think, okay, maybe it's missing some forcing, the slow forcing. Maybe the sun is not interacting properly with the atmosphere. Maybe you're talking about deep ocean circulation that connects things in the slow time scale. So, in other words, you're looking at this end of the spectrum, thinking that the problem in your model is here. But quite often, the problem is not there. The problem is in the higher frequency that is not properly connected to produce this impact on the low frequency. If you connect to Carlos Haupt's paper, for instance, he connects the diurnal to the intraseasonal. And then it became quite clear to me that, well, we're not doing that great in the diurnal variation as well. Most of the models, for instance, they have a hard time predicting the timing of convection in the Amazon, for instance. Most of the models in general have not enough amplitude in the diurnal cycle. The phase is also a problem. And when you're talking about nonlinear interaction, the phase is also important. So sometimes you have to go back to more basic things in your model in order to solve a problem in the slow variability. And a proof that this is probably what's going on is the fact that if you have enough computer power, like a zillion processors available for the simulations, you can actually model the whole globe with a few kilometer resolution. And these models perform much better than the coarser resolutions, but those very high resolution models are still not feasible for operational purposes. So I think we really need to explore in more detail the mechanisms for this kind of connection and find the causes of why it's difficult to predict.
Can you go back?
Mm-hmm.
So this is the result of a model, right?
Very simple. That's this too shallow water.
Yes. The question is, how do you know if this model is correct or capturing the right?
If you stay for my talk in the monsoon circulation, I'll talk a little bit about this. Actually, we're capturing things that look reasonable. You know, the structure of these.
Can you compare this to data?
Paleoclimate data. That's the talk in the afternoon. Okay. Yeah. More recently, I've been very much interested in the multiscaling problem, the interaction between what's called the QBO, it's a 2-year phenomena in the stratosphere, and the intraseasonal oscillation. We just submitted this paper recently. So I think there's a lot of work that can be done with very simple model. This is a very simple model, again. But in spite of all these problems, we're doing pretty well in the sense that if you look at the ability of the European Center for Medium-Range Weather Forecast in a consortium in Europe, that's a measure of accuracy of the forecast, the 3-day, 5-day, 7-day, 10-day, and it's usually believed, and that's the score above climatology. In other words, if you just use statistics, you would get 0, right? So if you get anything beyond climatology, that's this measure. And northern hemisphere and southern hemisphere. The northern and southern hemisphere used to have a big difference up to the early 2000s. And then from 2000 on, things improved a lot. And the reason is actually data simulation. Data simulation techniques. And the paper was published in 1986 with a method by a guy called Lorenc, not Lawrence, Lorenc. He published the paper, the theoretical paper here. This method became operational here, basically because of the computational power demanded for this kind of analysis of data simulation.
Doesn't it also depend on data collection?
No. Actually, they use the same system with the data stored in their system from the late 70s, early 80s, and you have a major improvement. Actually, the surface data is worse now than it used to be back in the 70s. However, you have more satellite data. But the satellite data, you have issues about representativeness and so on. And nowadays, performance in the northern hemisphere and southern hemisphere is pretty much the same. So back to this issue about dealing with initial condition. So you have different types of data. The surface data, as I mentioned before, deteriorated. You don't have as much data as you had back in the 70s, for instance. However, the satellites, that's a huge amount of data. You have hundreds of petabytes per year. And the principles of what's called the four-dimensional data variational simulation is to, you have a model, and they're actually not just using the data at t equals 0, or a window around t equals 0. You're actually using the past. So you're continuously adjusting the analysis to the observed data, considering the errors in the model and errors in the observations. You have to consider both. And you have to deal also with the model uncertainty, as I mentioned before. So how we deal with this kind of uncertainty? With ensemble forecasting. So you do several integrations. This is costly. Costs a lot of money. So what the World Meteorological Organization does is coordinate an effort involving the world forecasting centers. You have about a dozen centers all over the globe now. And these guys, they produce forecasts and they put it in the system, and lots of petabytes that you have to circulate around. And that's the kind of information that's used in order to extract a probabilistic forecast based on different models and different initial conditions. And of course, there are issues about what's a good ensemble. Here's the control, the average, the truth is here. This is a good ensemble. But sometimes if you don't perturb in a wise way, you may eventually get way out. We got into this business that about 15 years ago with this program of model intercomparison. We put together a supermodel ensemble for South America. These are observational stations in South America. And we started out using a Bayesian approach. And we put together, this is a page, it's open, this page. When you talk about the forecast in São Paulo, for instance, there are probably 70, 80, 90 forecasts. And then after using Bayesian averaging, you can actually compute probabilities of occurrence of different phenomena for temperature, for precipitation, and so on. And extremes are very important from the applicational point of view. But add more members, improve things, but it's very high computational cost. And more recently, there is a lot of interest, instead of using Bayesian techniques, using ensemble Kalman filters. But in last 10 years or so, we've been experimenting with different types of artificial intelligence. When I was at LNCC, I had a PhD student there, Amanda Dufek. She used genetic programming to compute the weights associated to each model in order to improve the probabilistic forecast. And she actually showed in this paper that you can improve upon the traditional Bayesian approach. More recently, my wife had a student who worked with deep learning. He also made an improvement, less costly than the genetic programming. So that's basically what people have been doing in order to deal with this issue about the model uncertainty. In other words, there has been growth in a number of papers that use some kind of artificial intelligence, not in the original data, but in the model output. And that, I think, is quite reasonable. If you talk to, sometimes you talk to people in the computer science, they think that the artificial intelligence could replace the dynamical model. But in practice, that's not what is happening. What is happening is as if you use artificial intelligence procedures on the dynamical models, the products of the dynamical models, you tend to improve the forecasts. And users are now more familiar with the use of probabilistic forecasts. For instance, the energy sector here in Brazil, I'm really surprised. I mean, quite often we have meetings with these guys. You sit at a table to talk about, they are concerned about the fact that there is uncertainty in the forecast. But then when you introduce yourself and the guys in the energy sector, quite often you're talking to someone with a PhD in data science, in other areas. I feel extremely happy nowadays to go to these meetings and see that, you know, at the private sector, you have people who are, you know, familiar with the fact that you have uncertainty. Because I have an episode about 20 years ago at the National Operator System, the energy, ONS here in Brazil. And I talked about ensemble forecasts. It was 1996. At the end of my talk, this guy tells me, Professor, very interesting, your talk, but we need one forecast. No way, right? But now they use it. So it took more than 2 years, but they're using it. And I'm very happy with the fact that people are aware of the fact that you have to deal with uncertainty. So the current trend in the energy sector is what's called the S2S, sub-seasonal to seasonal, 20, 30 days to 6 months forecast using these concepts of ensemble forecasting. So they're connecting, you know, the weather forecast to the seasonal forecast. And the S2S is right here in the middle. And it works because you have the predictability dependent on the purely atmospheric processes up to a few days, land processes between 70 and 30 days or so, basically due to the role of soil moisture as a memory driver, and then the ocean. So, and I like this kind of simple model work because you can actually deal with the mechanisms involving the connectivity between these scales in this multi-physics model. Otherwise, you have to use these very complex models that are used for operational purposes, but it's hard to understand exactly what's happening there. So I really encourage the young generation to explore the use of the simplified models. It's a problem nowadays because if you want to publish papers, it's much easier to get one of these complex models, plug a few numbers, change parameters, and see what's happening, and you have a paper. But working with more theoretical models require a substantial amount of work. You know. And but you know the system is very tough. Okay, and of course the use of higher resolution models, which is very nice nowadays. We can do some very interesting things with cloud resolving models, like this and this one. This is a high resolution model, so it looks more like that one. That's an Amazon and the clouds evolving the Amazon. This is a coarse resolution model. Doesn't look at all similar to what happens, but this is more close to reality. So we have the ability to use high resolution models. It's an enormous effort from the computational point of view. So I think that from an energy point of view, we went from a single forecast to the probabilistic view in 20 years' time. There's a growing perception of the complexity of the environmental system from different sectors, like the energy or the agribusiness here in Brazil. A growing concern about environmental impact, and the models can be quite useful for that. And the experience with the undergraduate and graduate program at EAG-USP it's showing that nowadays most of our students, they end up in the private sector, working in these companies. Back 20 years ago, 85% of our undergraduate students stayed for the graduate program. Now it's the reverse. So, okay, so that's the summary. Okay, thank you.
So questions for Pedro? Yes. Students, good.
How long does it take a typical simulation to run for forecasting anything, in a CPU? How long does it take?
How long does it take?
Yeah.
There's a rule of thumb for the global forecasting centers that a 10-day forecast should take no longer than 2 hours of CPU
2 hours
time.
for 10 days.
Yeah, 10 days, 2 hours. In fact, that's for very high resolution. That's when at the ECMWF, for instance, they're talking about 10-kilometer global resolution. But the ensembles are generated at a lower resolution. ECMWF, for instance, the ensemble is at a 20-kilometer resolution because you have to make hundreds of simulations, and it would be not feasible with the really high resolution. High resolution is usually known as the control forecast.
And I suppose you run it on a big cluster. Like, how many cores do you have to run that?
Well, I can tell you, I was involved in a project, the parallelization of this model that produces those clouds in the end of the presentation. It took us about 3-4 years to go from 600 cores to 20,000 cores. A work based on a group of about 5 people. And nowadays, ECMWF, for instance, they are running close to 1 million.
Yeah.
And we have to remember that this is a hyperbolic problem. So parallelization in general is not so simple in the sense that there is, if your strategy for parallelization is based on the model domain decomposition, you have a transfer of information from one processor to another, and that's what kills you. Santos Dumont CPU is about 25,000, but GPU is more than 1 million. And now that they're just putting together now the upgrade of Santos Dumont. Santos Dumont, the original Santos Dumont was 1.2 petaflop total. The upgrade now takes it up to about 6-7 petaflops. It's going to be the largest now, but right now there is a larger computer at Petrobras, 1.4, 1.5 petaflops, and Cimatec. Are you familiar with Cimatec? Is a research center, Senai Research Center in Salvador. It's the best example that I know of interaction between academic community and private sector. I don't know of anything here in Brazil better than Cimatec. Cimatec is, for those who know something about the German system, the Fraunhofer Institute. It's our version of the Fraunhofer Institute.
And just one more thing. For what you're showing, you have many differential equations you have to solve, right? So the initial conditions you have to give to the equations to solve them. Did you get them from satellite data or what?
Satellite data, yeah. Basically, satellite data is, now you have all sorts of sensors. And so you have an estimate. It's perhaps not accurate, but you have an estimate. And that's the trick, how to deal with an observation. First of all, what you measure is not exactly the model variable, right? So you have to have an operator that takes the model variable to what you measure and the inverse of this operator in order to deal with this problem.
I have a question. I have actually two questions. Actually, my first question is I would like to understand more your model. You have a bunch of differential equations, right? And you need to solve. And but I would like to understand how do you construct this differential equation? Where does this come from?
The equations?
Yes.
Basically, conservation principles. Momentum, heat, water, CO2, whatever, right? So it's basically conservation equations. And, but the trick is how to deal with the so-called, the smaller scale phenomena that are not resolved by your model. For instance, if you have a, let's exaggerate, you have a 20 kilometer by 20 kilometer grid. But you have lots of clouds in here that are much smaller. So you have this issue about upscaling. And that's the difference between model A, model B, model C, is how you deal with the multi-scaling parameterizations.
So my second question is, actually, I would like to know, do you know if there is, in your calculation, there is some stochastic process?
Yes. Actually, in the generation of the ensemble forecasts, that's something that's quite useful, is to introduce stochastic perturbation in the forcing terms on the right side of the equation. Yes. And that is how the ensembles, at least part of the ensemble, is generated through the introduction of stochastic forcing in the model. And there are lots of very interesting papers discussing the theoretical aspects of the interaction between the stochastic forcing and the slow manifold, for instance.
Further questions?
There's a question up there.
Yeah, you told us that using machine learning techniques
Yes.
on the outputs of the model is better to use throughout the process. But how well does using machine learning to do the whole forecast performs
not
nowadays?
successful, except for very short range forecasts. What's called nowcasting. Nowcasting, yes. You forget about the conservation principles, throw it away, and just use the radar data or satellite data, surface data, whatever is available. And then you get results that are quite good. Actually, if you could wait for a 4-hour forecast, 3-hour forecast, if you could wait 6 hours perhaps, you could get a very good forecast with one of these very high resolution models. But I don't think nobody would like that, right? So for what's called nowcasting, artificial intelligence is the thing now.
So we don't need any models anymore, right?
At least for the 3-hour forecast, 2-hour forecast, it's hard to beat, you know.
It's hard to beat.
Hard to beat.
Okay. So if there are no further questions, let's thank Professor Diaz again.
Okay, thank you. É incrível.
Você todo o negócio de como treinar a rede, essas coisas.
É.
Essa é a parte